We move to the next session. So the first session had two talks on deep existential questions like perception and the direction of time. These two talks are seemingly mundane. The first talk is about toothpaste, and the second talk is about shoelaces. But we'll see that these seemingly mundane ideas contain deep, beautiful ideas. So we invite our first speaker, Professor Guru Coomaraswamy, who's a chemical engineer by training. He works at the National Chemical Laboratory. He's been there since 2001 as a faculty member. He got his BTech from IIT Bombay in chemical engineering. He got his master's and PhD from Caltech. And he has been at the National Chemical Laboratory since 2001. He is passionate about scientific outreach. For the past 10 years, he's been part of an organization called Exciting Science Group in Pune, and they conduct lots of science activities for school students in particular. On that note, over to you.
Thank you very much. I'd like to begin by thanking the organizers, Math Science, for inviting me. This is a wonderful opportunity to connect with a very diverse audience, and I'm looking forward to telling you more about what we find fun and exciting in our group. And I'd like you to thank for staying on after the refreshments as well to hear more about materials. Like Ganesh mentioned, I'm a chemical engineer by training, and what I'm passionate about are materials, right? And these might be seemingly mundane materials. I'm going to specifically talk to you about materials that we work on in our laboratory. Some people call them complex fluids, some people call them soft materials, but I'm going to tell you about the structure in these materials, and specifically I'm going to focus on how these structures respond when you put some forces on them, right? So one of the most fundamental things that we do with materials is we look at the structure of these materials and how they respond to the flow that you put on them, right? So we're going to talk mostly about these kinds of materials. I just want to sort of comment before I start that chemistry is really a central science, right? I'm a chemical engineer. I work in the National Chemical Laboratory. And chemistry is really what connects the really complex materials of the kind that Shubha spoke about in the first part. And it connects it using the principle of physics that Rajesh spoke about in the second half. It's sort of interesting. I noticed that just to make sure that we have maximum entropy, we have one speaker from Maharashtra and one from Tamil Nadu in the first session, and another speaker from Maharashtra and another speaker from Tamil Nadu in the second session, also one from Caltech and otherwise. So it's kind of interesting. So let's talk about materials. And I'm going to start off with some very basic definitions just to make sure that we're all on the same page. So I'm going to talk about materials, I'm going to talk about structure, I'm going to talk about how the structure responds to forces that you put on it, right? So let's start with thinking about what we already know about materials and how they respond to forces, right? So one canonical material is sort of a hard material, right? So if we take a material such as this that might make several of us very glad, this is an example of a hard material. And so if I want to think about common ways of describing this, I can think of these as firm or rigid or solid materials. And what that really means, it's a very simple concept, is that if I take this material and try and deform it, I need an enormous amount of force, right? So that's just sort of a definition to keep in mind. You can also have materials that are soft solids, like this sponge ball, this sort of smiley face that my kids love playing with and sort of compressing. And so these are materials that are relatively easy to compress. And what that means is relative to the hard materials, these are materials that you can compress or deform with a relatively small amount of force. So in school, we've talked about how materials can be thought of as solid, liquid, or gas, right? So we talked about solids and hard and soft solids. You can also talk about liquids, and an example of a liquid is really something that cannot sustain any force at all, right? So if I take a cup of water and pour water into a glass, notice that the water flows, and we all know this, we see this all the time. And more than that, it takes the shape of the container. So if you pour it into a glass, it takes the shape of the glass. If you pour it into a cup, it will take the shape of the cup, right? So these are materials that cannot tolerate any force, absolutely. Okay? And so we have talked about this continuum of solids, liquids, and gas. I'm not going to talk about gas so much, but I'm going to talk about materials that don't really quite fit on this discrete structure. There's really a continuum of states between these. I'm going to talk about materials that lie between those. And these are common materials, mundane, so to speak, but these are materials which have very interesting properties that don't fit into just the solid or the liquid kind of transitions. I'm going to talk about materials which have very interesting, unusual properties that lie between these. So let me take the first example. This is again commonplace example. We've all seen this. We've all been frustrated by the fact that when I take a bottle of ketchup, it doesn't flow, right? So if I take this bottle of ketchup or this tube of ketchup and I try and invert it, the ketchup will not flow until, and it doesn't really matter whether this is shaken or stirred. I think it's good both ways. But you can take this material, and if you have to really aggressively agitate it, then it flows, and then it flows like a liquid, right? And so here is a material which in the normal sort of state, when you take this bottle in and you invert it, behaves sort of like a solid. It doesn't flow, but then when you shake it, and so I'm going to use this term in my talk, this term shear, and just think of shear as a force, right? So remember my talk is about structures, forces, and how the structure reacts to the forces. So I'm going to use the word shear sort of interchangeably with force in my talk. So these kinds of materials are reasonably common. Right? They're called shear thinning materials, and what that means is that in the normal state, these are materials that do not flow, but when you force them or you shear them aggressively, then these are materials that will flow sort of like a liquid, right? Now these are really not uncommon materials. They're not unusual. We see them in many, many instances. And this is something which we use technologically. It's an extremely useful property. So if I take something like paint, right? So I take my brush of paint, right? And then when I brush it on the wall, the paint flows. And that's important because you really need it to flow when you brush it on the wall. However, when you take the brush off the wall and this fluid on the wall now is at rest, it thickens up, and then as a consequence, it doesn't flow anymore. So this is a very useful property, and we see it in things like ketchup, we see it in things like paint, we also see it in things like toothpaste, right? And so we're all familiar with the fact that if you take a tube of toothpaste, it doesn't flow out until you squeeze it out, and that's a very useful property for toothpaste to have, right? Now, I'll come back and talk about this. If I have this very abrupt transition, right, when I take, for example, in toothpaste, the stuff that flows out is this jelly kind of material. You put it on the brush, and when you brush it, and then it really flows very rapidly, right? And so, sort of a very abrupt transition between a solid-like state and a liquid-like state is called yielding. We'll come back and talk about this in just a little bit. So, if I think about making materials, right, and that's something that we love to do in our laboratory, how do I understand the structure that gives rise to these kinds of properties? So this is kind of intuitive if you think about it. So if I take a material, say like toothpaste, and this is a theme that you'll see in many of the structures that I'm going to talk about, what you have in there in many instances is small particles, and the particles in the normal state will link up to form these thin networks. Right? The consequence of having these particles form these networks is that if you try and flow it, the network takes the force and it doesn't flow. Right? And so you have a material which you have where you have two kind of components to it, a fluid component and these particles that are held together to form a network. But then if I shear it, or I shake it, or I stir it, or I brush it, or somehow get aggressive with it, then you can break up this network and you have these particles that float around in this liquid, right? And so consequence of that is you go from this network state to a state where these particles are sort of floating around in a liquid, and this will flow, right? And so that's what I mean by a complex fluid, in that this fluid has inherent in it structure, right? And the structure might look like this, or it might look like this, and you can transition between these two states by putting some force on it. Okay, and that's really the kind of thing we're going to talk about. And so this is an example of a network structure that might break up on agitation. Okay, now this is not a purely academic question. And so concepts such as this, where you have a transition from a state which is fairly rigid to a phase which flows, can have very important practical implications. So here's a video of something that happened off the coast in Britain. And so you have a cliff, you can see something pretty dramatic happen all of a sudden, right? So this is a yielding transition where you have the particles of soil and stone that are put together to form this cliff, all of a sudden realize that it can't take its own weight, right? And that might happen as a consequence of maybe being soaked by the humid wind. It might equally happen if you trek in the Himalayas in the month of August when it's rained a lot, right? And so you have landslides like that. And this is something which is extremely important for, let's say, public administrators, people who'd like to make sure that other people get out of danger when they need to. Now, how do you try and control it? It's very hard, right? So you can try and put up scaffolding, you can try and put up other structures in place that will hold this together, but this is really something which is very hard to control. So what we're trying to do in this instance is try to understand the structure of the materials, the structure of the soil, and what is the network that holds it together, and when is it expected to fail. Okay, so that's something which we really can't control, but if you could control it, what can you try and build with it? And that's the kind of question I'd like to ask as an engineer, right? So I'm going to take a moment to try and make a connection between these kinds of rigid to soft transitions and soft robotics. Right? Have you heard of soft robotics? Thought in passing, you've not heard of it at all. So, one of the things we'd like to do as we go towards more automation is to make robots, things that will do repetitive, multiple things with a great deal of precision. Actions like picking something up and putting it somewhere else. Now, if you think about it, this is something that we do with great ease, right? So I can pick up, let's say, a bottle of water from here, move it around and put it somewhere else, right? Or I can pick up something which is a little more delicate, right? I can pick up this thing and move it around and put it somewhere else. Now, for a robot to do this might turn out to be really hard because the hardness or the weight of this material is very different from maybe the softness or the weight of this material, right? So if I had to pick up something which were very delicate, right, and I have a robot that's used to picking up steel barbels and moving them, you might just end up crushing that object. And yet, when we do it, right, and this is amazing, this is the biology that we know exactly how much force to exert, and we have all the sensory perception that gives us feedback telling us we're pressing too hard, right? We can do this very easily, while a robot might not be able to do that. So what's the connection, right? So you try to make, one of the things you try to make are things that can emulate biology. So you make things which are soft robots, right? And a beautiful example that came out recently, this is from a group at the University of Chicago. This is the group of Heinrich Jaeger, is this beautiful example where they built what they called a universal gripper, right? And I'll show you a movie of this. So this is a very simple device. You have a plastic bag, and in that plastic bag, you put a bunch of particles, right? Sand particles like dry sand. And so this thing flows if you try and push it a little bit. It's not a really well-packed object, and it flows very readily. And so if you can take this and you bring it close to some kind of an object, then it sort of flows around it like it would if it were a liquid, right? But then what they discovered is that if you change the pressure of air inside that bag, so this gripper is connected to something that's like a vacuum pump, you pull a little bit of vacuum on it, and all of a sudden, right, these particles rigidify and form this nice rigid structure. And so you have this thing that flows around like a liquid, and then you can rigidify it and then pick it up and grab it and move it along, right? Very simple concept, but the background that goes behind this is this detailed understanding of what leads to network formation, what leads to this kind of structural formation in these materials. So let's take a look at a movie from that group. This is from a paper that came out about 5-7 years ago. And so this is this universal gripper. So you see you have this plastic bag that comes in. You can go down, grab something that looks hemispherical, move it around. You can also pick up something which is soft, like a ear plug, move that around. You can pick up something that is fragile, like a light bulb. No problems, you can move that around. In fact, you can pick up something which is even heavier, like a shock absorber, weighs more than half a kilo, and move that around with the exact same arm. And this is my favorite example. You can pick up a raw egg, which is really a delicate object. Just to convince you that that is a raw egg, you can see that it's broken, right? And this is amazing. You can pour water with this. We take this for granted that you can pour water, but this is a fiendishly difficult thing to do, right? This is absolutely amazing, the fact you can pour water using something like this. So a very simple concept, the idea of being able to control this rigid to soft transition. This is not something we can control in nature, but if we can learn from that, and if we can figure out how to control it, you can build incredibly interesting engineering devices out of that. Okay, so let's move on. Some of us who are of a certain vintage might say that we've watched this movie and we remember this scene, but for the others who've probably not watched it, let me play this. This is, by the way, from a 30-year-old movie, sort of a very soupy, romantic musical that came out some years ago. It's from a movie called Mella Tharandhathu Kadave. And some of you might remember this or might admit to remembering this. So it gets more gory, so we'll stop there, right? So one of the things that you learn when you're a scientist is that you need to be irreverent, right? You don't have to respect all the conventions and maybe even subversive a little bit. So I thought, where am I going to get an opportunity to play a clip from this movie at the Sabha, right? So, but anyways, turns out that this is actually a fairly interesting material, right? And so what you saw there was quicksand. So I went on to Wikipedia and looked at quicksand. So quicksand, Wikipedia says, is a colloid hydrogel consisting of fine granular materials such as sand, silt, or clay, and water. It's absolutely accurate. It doesn't really tell me very much if I don't know what those terms mean. So I went to dictionary.com, and basically what it tells me, it's loose wet sand. Okay, and that's loose wet sand that yields easily to pressure and sucks in anything that rests or falls on it, right? And that's really what we saw also in the movie clip. So let's go back and take a look at that a little bit more carefully and to try and understand, does it really suck it in? Can you get sucked into that and go inside and, what we saw in the movie? Is this really an accurate way of describing quicksand? So before we go ahead, I thought I'd show you a very nice clip to tell you what quicksand is all about. So indeed, quicksand is loose, wet sand. And so the loose part is also kind of important. And so you have here a video where you have loose and you're sort of loosening the sand. So it's not just sand and water, it's sand and clay and some salt water, and I'll not tell you why. And then you can put a metal object and it actually rests on that, right? And not if it were much heavier, but now you put it on what's called a shake table, and that's something that will simulate an earthquake. And so what you notice is that if you start shaking it aggressively, all of a sudden it behaves like a liquid and this stuff sinks in. Right, and that's quicksand. So let's get back to this question that we asked, which is, can quicksand literally suck you in? Okay, can you go into it all entirely? So loosely speaking, it's basically loose sand saturated with water, and there's a little bit of clay and salt, and that's important for the structure. I won't get into the details right now, but that's important to create this very interesting structure that's quicksand. And so one of the things that we saw is that if you put a huge amount of weight on it, and so you stand on it, it will yield. So essentially, it's very loosely connected sand with a lot of water. It's saturated with water. And you see it, for example, in situations where you have water flowing up into sand. And so in situations like that, the sand grains move apart, and salt is useful in that context. And then you have a lot of water around it. So if you stand on it, boom, you go in, right? And the other thing we saw, as we saw in the movie as well, is that the more you thrash around in this quicksand, the more it forms a liquid-like state and the more you sink into it, right? So the question is, can you completely drown in quicksand? Now, let's think about this a little bit, right? Let's look at the physics of this question. Now, what we are made up of mostly, right? There's all this interesting stuff, the biology that goes into it, but most of our body is really water. Right? So how dense are we? We're roughly about as dense as water, right? Which means if I take a situation where I have water with a lot of salt in it, that's all I'm putting into it, right? I'm dissolving salt into water. As I go to the Dead Sea or the Red Sea or one of these places, I can't sink, right? Because my body will float on that water, right? And so you have a situation where you have water plus salt and you're going to float on it, right? Now, quicksand is water plus sand and clay, and sand and clay is way denser than that, right? And so what that tells you is that the probability that you can actually get completely sucked into quicksand is nearly zero, right? It's sort of like the probabilities that Rajesh spoke about. It's not going to happen that you get sucked into quicksand, right? Because you're far less dense than quicksand is. And this is, you don't have to take my word for it. This is something that a scientist did in the Netherlands about 15 years ago. And so by the way, this is the kind of thing that we do in the lab, right? So we get toys and you put them on quicksand and you shake it to see what happens. Actually, this is a fairly serious investigation. This scientist, Daniel Bourne, was in Iran with his wife, who happens to be from Iran, and noticed that there was quicksand, so he scooped it up, brought it back to the laboratory to go back and study this problem, right? And what he did is he took a toy, and this toy has roughly the density of a human being, so it's roughly the density of water, and then when you put it on this quicksand and you shaking it, sure enough, you can see that this toy will go in, but you can never get this toy to go in completely. It will only go in to a certain extent, and then you'll stop there. So what we saw in the movie, well, wonderful drama, but not entirely true. Okay, so but the second part of it is more interesting, because what if you go back and think about quicksand, once you have the misfortune of falling into quicksand, you're not going to simply drown and get into it. However, getting out of that is much more challenging, right? Suppose my foot goes somehow into quicksand. I'm trying to pull it out, and I'm pulling it out with about 1 centimeter per second, right? So this is roughly 1 centimeter per second kind of a speed. Now, if I try to pull it back, turns out that the force that holds back my foot when I try and pull it at this speed is roughly equivalent to like a weight equivalent to a ton that hangs off of it. So it's like a small Maruti car or something that's hanging onto my foot. So once you get into quicksand, getting out of quicksand is far more difficult. So if you get trapped in it, then the chances of you not being able to get out and then starving to death or something is more likely, right? So getting into quicksand is you can see that it liquefies, but it's really hard to get out of quicksand. A question that I'm going to ask is, why is that? Because that tells us something about structure. What I know is that if I learn something about structure, there's something useful that I might be able to make out of that. Okay, so let me ask this question. So turns out that quicksand indeed liquefies a little bit when you at first, but subsequent to that it thickens, right? And so this is something which makes it very difficult to escape from this quicksand, and this is a phenomenon which is sort of opposite of what we looked at earlier, shear thinning. So here, if you put a lot of force on it, it actually thickens on you, right? And I'll give you an example of something like that. This is not quicksand. This is a material that's made by one of my colleagues, Dr. Badigar, and this is a sort of a molecular version of this material. So you notice that this is a material that flows. It flows like water, but then if you shake it very aggressively, lo and behold, it becomes something which is a rigid ball, right? So this is a material which is shear thickening, in that it's kind of a more unusual phenomenon, that if you shake it aggressively, it becomes stiffer. Now, what possibly could be the structural origin of shear thickening? So let's take a quick look at that. So shear thickening, we don't entirely understand how shear thickening works, but what we believe happens is that if you start off with a structure where you have these particles floating around, when you shake it aggressively, if for some reason these particles tend to form clusters, and then the clusters link up, that's really what gives rise to shear thickening. So shear thickening really arises from the tendency of these particles to form clusters if you aggressively shake it. Okay? So let me show you what we can make out of this that might be interesting. So I'm going to talk to you about a material that we use fairly commonly in the kitchen as a thickener, which is cornstarch. So I'm going to talk about cornstarch and water. And cornstarch really contains grains of starch. They contain, starch is typically amylose and amylopectin. So basically you have grains that can sort of hydrate in water. Okay? Very commonly when you go back and Google this, cornstarch and water mixtures are called oobleck. We'll come back and think about why that is. We'll talk about why that is the case. So let me show you again sort of an interesting video of what happens when you have cornstarch and water put together. Right? So here is water and here is cornstarch, fairly large amounts of it, and you can see that they both flow. This is about 1:1 cornstarch to water. And then if you drop something heavy like a metal wrench on it, what you see, it sinks immediately into water. This is the same movie in slow motion. You notice that when it hits it, it kind of bounces off. right, of the cornstarch, and then once it sort of settles down, it slowly sinks into this material, right. So at high shear, it sort of bounces off like it were a solid object, right. You can try and really get aggressive with it. This is a wonderful way of relieving stress, beat up on cornstarch. And what you notice again is that this cornstarch water mixture is able to take the, you can't put your fist through something like that, while on the other hand, you just punch through water, right. In fact, this is even more impressive if you have a real gun and then you take a small plastic bullet and try and shoot it through this mixture of cornstarch and water. Let's see what happens there. Boom, doesn't go through, right? And then it sort of slowly flows back as if it were a fluid, right? So you can see that again in slow motion. This is like a soap opera. We see it and then we see it again, right? And just to make sure that you believe that this is really shooting with a fair amount of force, you can actually shoot through the bucket and the water will simply drain out of that bucket. So this is something that you can see in this material. So very interesting material property, which is very different from what you see with ketchup and so on. So oobleck, right? I thought this was interesting. So many years ago, Dr. Seuss wrote a book called Bartholomew and the Oobleck, where the oobleck is a green sticky substance that sort of falls from the skies and sticks to everything and makes life in the kingdom miserable. And so somehow the science nerds got hold of that, and now in the literature very often cornstarch and water is called oobleck. Right? This is an interesting aside. So if I wanted to make a material that would shear thicken, then one of the things I might want to do is to enhance the tendency of these particles to try and form clusters. So here are my particles that are floating around, and one of the strategies I can use is to take a string-like molecule that ties these things together to form a cluster. So I have a material such as this string, and I want to make this string such that it's slightly attractive, it slightly wants to stick to the particle, and then when I force it a little bit, this unravels because of the force. These things are not very strongly sticky, they come off a little bit, and then if I force it some more, they go and grab onto another particle, and then they start forming these kinds of clusters. Okay, so can you make these kinds of things? What are these molecular strings that one can use? We'll come back and talk about these molecular strings later. So these are materials that are called polymers. I think Rajesh spoke about them briefly in the last talk. I'm going to tell you why they behave sort of like molecular rubber bands that tie these things together. Okay, but what can we make out of if we try and use this idea? Right? And this is some work that was done again about 10-15 years ago from the University of Delaware. This is a group of Norm Wagner. And what he did is he took 3 layers of nylon and actually shot a bullet through it. Oops, let's play. Right? As you try and shoot a bullet through it, I mean, this is what would happen if you were wearing 3 layers of nylon and somebody shot a bullet through that, it just goes through. Right? That with disastrous consequences. Now, you take 2 layers of nylon and you sort of dip it in shear thickening fluid. STF in this case is shear thickening fluid. So you dip it in this STF, you have a nice lightweight nylon jacket. What we can see here is that now if you try and shoot a bullet through that, it actually bounces off. Right? This is absolutely incredible. Right? All you're doing is taking the shear thickening fluid, dipping nylon sheets in it, and it bounces off a bullet. That's mind-blowing. So the shear thickening fluid that was used in that case is again a very simple material. It's silica or sand particles and a little bit of a polymer. Right? And the polymer that they used in that case was something called polyethylene oxide, but that's a polymer that sticks loosely to silica, and that material then allows this silica to bond with each other, forming this molecular tie, and that results in the strong shear thickening that you see in this material. So that's good enough to make then a bulletproof vest. So a consequence of understanding how to control structure in this then allows us to make lightweight, stab-proof jackets, bulletproof vests, and so on. Bulletproof vests made of Kevlar and so on are really heavy objects, right? This is a very nice alternative that is currently being developed by many people around the world. So we spoke a little bit about polymers. Let's come back and think a little bit about what a polymer is. So a polymer is really a long string-like molecule made up of units, right? Each of these units is called a monomer. So if I have one unit, I have a monomer. I attach another one, it's called a dimer, trimer, and then I make a long string, and that's called a polymer, right? And we can make these strings out of many different kinds of units, and the different units give it different properties. But if I take a flexible, long, thread-like object that looks like that, what we've studied is that it makes this entire object behave sort of like a spring, like a molecular rubber band, right? And that gives rise to amazing properties, very, very unusual flow behavior. So before I run this video, if you woke up this morning and you had your tea or coffee and you stirred in your sugar into that, right? One of the things you notice when you stir in something into milk or water is that the shape of the surface of that fluid when you stir goes in, right? It's sort of a vortex that goes in. You've noticed that, right? Now let's see what happens when you take this stringy material. This is dye, but so just so that it's easy to see. And there's a water-soluble polymer that's put into it, a very long, stringy, flexible object. And then when you try and stir it, what you see is something which is very counterintuitive, right? It actually goes up the opposite way, right? And the way to think about it is really to come back and think about this polymer as this molecular rubber band, right? So you have this polymer, when you stir it, you're stretching the rubber band as it goes around along the flow lines, and as you stretch it, it's a rubber band, right? It wants to pull back, and as it pulls back, it pushes against this stirrer and climbs up on the wall, right? Very, very unusual, right? This is mind-blowing. It's a simple polymer and water, and you see behavior which you don't normally imagine. In fact, it gets even weirder, right? I mean, you can pull out this material, and what you're doing is there is a syringe here. You suck out a little bit of this polymer solution from this. So you pull on it, you can suck some of this stuff out. And remember, you're now sucking this string-like molecule, and that elasticity allows it to continue to flow, right? And in fact, it will continue to flow. This will overflow. You can actually drain this large material by simply pulling out a little bit of it. So very, very counterintuitive properties because we are not used to dealing with materials such as this. By the way, these videos are created by a former postdoc who's now at IIT Kharagpur, Professor Chirag Kalelkar is at IIT Kharagpur, and he's put together, these are all experiments that are known, but he's actually made these in his lab, filmed them, and he has a YouTube channel which has hundreds of these. So please go and view it. There's all kinds of very interesting videos on his channel, right? So that's a polymer. So let's sort of try and put all of this together, right? So we're talking about properties of materials that come from structure, specifically looking at the flow properties of these materials. We talked about shear thinning materials, we talked about shear thickening materials. In both those cases, including, for example, for the shear thickening fluid, what we saw are composite materials, right? So composite is materials in the shear thickening case where you had hard silica particles that you put together with a soft polymer. And again, you see this emergent property, right? So the hard particles, you don't expect that they'll do all these weird things. The soft particles, the soft polymers alone, you don't expect that they'll do these weird things. But put them together and you get a property which is completely unexpected. And that's what we call an emergent property. And in this case, what we saw was that the fluid that you got would start shear thickening. So in general, one can design composites so that you can combine the best of two worlds, right, by taking solid and liquid and making interesting new materials out of those. So let's go back to nature and see what we can do with composites. So here's an example which I love, right, seashells. Most of the seashells are mostly comprised of a material called calcium carbonate. Now calcium carbonate is the same stuff as chalk, right? And you know that if I take a piece of chalk, I can snap it really easily, right? On the other hand, it's extremely hard to take a seashell and break it open, right? And that's because if you go back and look at the structure of the seashell, mostly, so I've taken a piece of seashell and this is an electron micrograph to look at it in more detail. Each of this is about 0.5 millimeter. Each of these plates is about 0.5 millimeter thick. And so what you have then are plates of calcium carbonate separated by a tiny bit of polymer. That polymer is about 2% of the weight of this material. So it's 98% rigid calcium carbonate with 2% of a protein, which is a soft sand. So it's like a sandwich, right? You've got these stiff plates of calcium carbonate that sandwich this soft protein. And so what then happens is that the way in which materials break is that, for example, if I take a glass pane, a crack forms and then the crack just propagates to that material. And if it's a rigid material, typically those materials are hard to break, but then they will break. When they do break, they're fragile, like glass, It's a hard material, but when you break it, it sort of just propagates down. Now, in materials such as this, the calcium carbonate part is sort of like glass. It will break, right? But as you propagate down through that, if I take a crack and I try and propagate it down through that, you suddenly hit this soft, gooey polymer. So the polymer can't really break. You can stretch it, you can pull it. All the energy that goes into that crack then goes essentially into the polymer, and you can't break this material. Right? So using this very simple idea of making layers of calcium carbonate and polymer, you can now make a material which is very, very stiff. Now again, we can learn from biology, and you can take this concept to make things like safety glass. Right? So if I take glass panes and I sandwich between two glass panes a sticky, soft polymer, in this case is a polymer called polyvinyl butyrol, then you can make materials where if you try and punch through a safety glass, I don't recommend that you do it. It's extremely tough. Right? It's very hard. It really has a lot of force. Also, when it does break, because you have this nice sticky polymer, you don't have glass shards flying all over the place. You have them sort of stuck to that. Right? And so again, concept that we take from nature, you can sort of implement and make these kinds of materials. So I want to give you one last example of what you cannot do with this. Right? One of the problems that we thought about when we started working on these composites is that seashells aren't flexible. Right? You can make these nice composite materials, but when I combine soft and hard, I'm not able to make a material which is mostly hard, but then it's flexible. Right? And that's something we started out making, and what we discovered is a way of making a composite material. So this is a piece of sponge, it's centimeters in size, and the sponge mostly comprises of these particles. Again, in this case, they are sand particles, they're very small, about a micron in size. So each particle is about 1/1,000,000th of a meter in size. And there's a tiny bit of polymer that goes around it, and it's so small that you can't see it on this electron micrograph, right? And so we make these materials, and if I take this sponge that you have on the top and you try and compress it, you get a material which is almost all solid, but you can compress very nicely. Right? It's a nice, flexible material you can make. In fact, you can compress it much more than this. You can compress it down to about 1/10 of its original size. Right? Fantastic new material. Now, why would you ever want to make flexible seashells? Right? Why would you want to do something like that? Well, turns out that once you know how to make these kinds of flexible structures, there's all kinds of interesting things you can do with it. For example, one of the things we've made is flexible devices that you can use to charge, for example, your cell phone. So if you want to make, we're all talking about flexible TVs. How are you going to make flexible power cells, right? How do you make flexible batteries, right? So these are the kinds of materials you can make with this. One of the other things we've done, and that's the beautiful thing about learning the physics of a material, is that you can then apply it across a wide range of materials. One of the other things we've done is to make biocompatible materials, which you can then sort of squeeze into a small object and do a very small surgery to insert them. We've done it in mice and so on. I'm going to tell you one other property you have with this materials, which I think you'll appreciate a lot better right now. So typically, if you have large auditoria like this, or you have airplanes, or you have public transportation buses, there's a very tight specification on the kind of materials you can use to make seat cushions, right? Because we are very worried about fire hazards. You make materials which are essentially fire retardant. And the way you make it is you take the polymer that you're using to make this foam, or the sponge, and you use some fairly nasty, environmentally damaging materials, things that contain bromine or phosphorus, but we need to do that because otherwise this stuff will burn too easily. Even a good quality fire retardant polyurethane sponge, this is one that's used in automotives, if you stick it into a direct flame, this is a temperature of about 1200 Celsius, will eventually burn and sort of peel off. Now, in contrast, the materials that we have are mostly sand. Sand's not going to burn, right? And so you have a flexible material which if you stick it in a flame really won't burn, right? In fact, if you take it off the flame will even self-extinguish, right? So sort of a practical thing that we can make out of it, including things like soft batteries, including things like things you can put inside with small surgeries. You can use the same concept to also make seats that you can sit on which won't burn even if they're subjected to a flame. So I'm going to sort of stop here and summarize. So what we've talked about are how you can use the idea of making composite structures and use these composites to control material properties. So if you can understand what goes into making a certain structure and how that structure is going to behave, you can then design these kinds of materials. We learn from nature. Again, as Shubha said, we can't be too proud of what we can achieve because nature does things which are far more complex. But we are learning from nature and we are using it to try and understand how to make these materials, and specifically what we are interested in, these kinds of soft materials. So with that, I'd like to thank and show you one last video of what might happen if you take cornstarch and you put it on a sound speaker. I don't recommend that you do it at home, but it's absolutely fascinating. Thank you very much for your attention.
Thank you very much for a hard-hitting talk. We have lots of questions for you.
Thanks.
And as I expected, everybody in the audience seems to commiserate with Amala. Everybody wants to know what was the right thing for her to do. What should you do if you're in a quicksand?
Yeah, actually this is, it's amazing. There's a lot of themes that revolve around quicksand. Unfortunately, that's kind of gone out of fashion, I think. But the thing to do is to just not thrash around so you don't sink in, and then very, very slowly get pulled out. Not even at a centimeter per second.
So you wait for Mohan, that's the
You wait for Mohan, yes, yes, yes. So I didn't want to agree, I didn't want to admit to have watched that movie, right? A horse can pull it out, very slowly though, right? If you try and pull it fast, then you just snap the person.
Without any more insults to Mohan, let's go to the next question. So this is a question from SMS from the phone number ending in 630, which asks, is the clotting of blood related to shear thickening?
No, that's an interesting question. And again, this is again an example of a soft material, but the clotting of blood actually comes because of something which is which I didn't speak about. It's a smart material, right? So when you have a wound, then sort of the body realizes that there is a cut, and you get exposed, you basically have something that's exposed, and a consequence of that is you start forming a network-like structure. So there is something called fibrinogen that sort of clots and forms a network-like structure, traps all the blood cells that can't escape, and then eventually that sort of dries out to form. So it's not a shear thickening material, but it's a material that forms a network on exposure to, in this case not force, but in this case exposure to an unnatural surrounding.
Thanks. So maybe a related question from Gopalakrishnan. Is shear thickening due to polymerization? Is it always due to polymerization?
No, so polymerization is adding different things together. So if you want to think of clustering as polymerization of particles, yeah, maybe it's a loose way of thinking about it, but polymerization is typically a molecular phenomenon where you add these monomers together. So shear thickening doesn't really come from polymerization. It comes from particle clustering in these kinds of situations. If you have very long polymers and you try, they're like spaghetti. So if you have very long polymers and you have just polymers and nothing else in there, those might also shear thicken, but that's really because you can't unentangle things.
Thanks. So in the interest of time, let's move on. Thank you very much again for a very nice talk.